Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be attempting to answer the question of how do we determine factors of a polynomial, in particular by using the technique of the greatest common factor, or the GCF. In this video, we're going to be analyzing the definition of the greatest common factor and using this definition to help us actually break down polynomials into two unknown factors. So the first thing that we need to do is understand what the greatest common factor is, or for shorthand, the GCF. Now, the GCF is determined when you have multiple quantities that you're working with or multiple expressions. So I'm going to say, given two or more quantities or expressions, because remember, we could be working with numbers or polynomials. So given two or more numbers or two or more polynomials, the GCF is the largest common factor that is a factor of all of the other quantities or expressions. Okay? If you have multiple numbers or multiple terms and polynomials together, the GCF is the largest of the factors that are shared between these quantities or expressions. So for example, let's take the numbers 6 and 15. What numbers are in common between 6 and 15? Well, let's list the factors. 6 and 15. 6 has the factors 1, 2, 3, and 6. 15 has the factors 1, 3, 5, and 15. So, of these, what are the factors that are in common? Well, we can see 1 is in common, and 3 is in common, but which of these is the largest of the in common factors? That's 3, okay? So the GCF for 6 and 15 is 3. If we went and listed a procedure for this, we could say that the first thing we need to do is identify the factors of each quantity. Identify the factors of each quantity. We would then determine which factors are common in both quantities. We would then finally determine of those common factors, we would find the largest common factor. We want the one that goes into all of them, but the biggest one that goes into all of them, okay? That's the GCF for dealing with numbers. Now, we want to also make sure that we're able to deal with the GCF when it comes to polynomials. Notice in this expression, I have 1, 2, 3 separate terms here. I have a trinomial. What we want to do is decide, well, what two things multiplied together to get us this trinomial? The idea is maybe there is something in common with all three of these terms. With each of these individual little expressions, the 4x to the fourth, the 2x cubed, and the 8x squared, maybe they all share something in common. Maybe they all have a GCF. So the goal is, first, is there a GCF of each of these individual terms? What I'd like you to do is pause the video, take a minute to identify to yourself, what do each of these terms have in common? Then we'll come back and see if we were able to find what that GCF was for not just the numbers, but these entire expressions. All right, well, hopefully you were able to work through this example. Notice that each of these quantities, the 4x to the fourth, the 2x cubed, and the 8x squared, they have both number and variable. When we want to find what's in common between all three of these, we're going to have to look at what's in common with the numbers and what's in common with the variables. Hopefully it was fairly easy for you to decide that what's in common between the numbers 4, 2, and 8. Well, that's just the number 2, right? That's the GCF of 4, 2, and 8. We could essentially factor out a 2 from all three of these expressions. But then it comes to the variables. What do all three of these expressions have in common with x's? Well, in the first term, there are 4 x's. In the second term, there are 3. And in the last term, there are 2 x's. So how many x's are there in at least all of these? How many x's do they at least all have? Hopefully you're saying that all three of these expressions have at least 2 x's in them. There might be 4, there might be 3, but all of them have at least 2 x's. So this is going to be the GCF of our polynomial. Let's go ahead and let's rewrite what we have going on here. We essentially are saying that we have taken 2x squared and multiplied it to some unknown quantity, some unknown polynomial, and we've ended up with a 4x to the fourth minus 2x cubed and a positive 8x squared. This is similar to work we did in our introductory video. You know what one of the factors of this polynomial is. We must have taken 2x squared and multiplied it by something to get this larger expression. But what was it that we multiplied it by? Well, an easy way of figuring that out is just dividing everything by 2x squared. And let's do that, right? Let's say that that unknown polynomial, well, if I multiplied 2x squared by something to get 4x to the fourth, what could that have been? Well, 4x to the fourth divided by 2x squared is just 2x squared. And then I have a negative 2x cubed divided by 2x squared. What could I have multiplied 2x squared by to get negative 2x cubed? Well, that would have just been a negative x. And then I had 8x squared. I multiplied 2x squared by something to get 8x squared. What could that have been? Well, that should have just been a 4. So this is going to be that unknown polynomial, the thing that we've multiplied the GCF by to get our answer. Let's go ahead and let's actually check our work. We're going to take 2x squared, the GCF, and we're going to multiply that by what we got when we divided our polynomial by that GCF. Let's see if this actually works out. 2x squared times 2x squared is 4x to the fourth. Then we have 2x squared times negative x. That's just negative 2x cubed. Then we have 2x squared times 4, and that's just going to be a positive 8x squared. What do you know? We have gone and we have taken the expression that we started with, that polynomial we started with, and we've rewritten it as the product of 2 other polynomials. We found that we can rewrite 4x to the fourth minus 2x cubed plus 8x squared as the product of 2x squared and 2x squared minus x plus 4. This is the idea of factoring by a GCF. We look to see, is there a number in common between all of these terms? Then we say, well, if there is, we must have distributed that term through to some other polynomial to get our trinomial answer, right? The only way I could take a monomial, 2x squared, and get some trinomial answer is if we distributed it through. So let's try to write down a procedure for what we have going on here. The first step is to identify the GCF. And let's actually go ahead and let's make sure we understand how we figured out what that GCF was. Because we had to do it in two parts. Find GCF of the numbers. So that was pretty easy. The 4, the 2, and the 8. We found a GCF there. Then we need to find the GCF of the variables. How did we do that? Well, we said there are x's in common with all of these terms. How many did they at least have? Well, we noticed that they at least had 2 x's in each. So what we're going to say is, to find the GCF of the variables, take the common variable with the lowest exponent. That's kind of what we did right here. We took the common variable x, because all of them had an x, and we found what was the smallest exponent on that. What is the lowest value of x that each of them share? That in turn gave us our GCF. Okay? Once we had that GCF, we divided it out from the entire polynomial. We took that GCF, and what we did was we divided it out from everything. You could also say we factored it out from everything. The idea of factoring is the same as dividing out, okay? So from each of those quantities, we divided it all by 2x squared. And then once we had our answer, once we had that missing polynomial, we wrote our solution as a product of two polynomials. So when we get our final answer, it's important that we write it as two polynomials being multiplied together, or multiple polynomials, I should say, being multiplied together, okay? Because you could have more than two. Right now, when dealing with this GCF, make sure you're comfortable with how to go about identifying the GCF. That's a very crucial step at figuring out what in fact the GCF is. Then, make sure you're comfortable dividing each term of the polynomial by that GCF. And please make sure at the very end you write your answer as a product. All right? Write that you took the GCF and you multiplied it by this quantity. You should get the original polynomial. It's very easy to determine if you have the right answer, because all you have to do is just remultiply things, just like we did at this part. We remultiplied to check that we had the right answer. That's what's really cool about factoring. You know in seconds if you did it correct or not. Let's keep this idea going, and let's try a couple other examples. And then I want us to answer the question of, when do we use this technique for factoring by a GCF? So first up, let's take a look at this trinomial, a bit more elaborate. It's multivariable. We have a 2x cubed y and z to the cube. We have an x squared, a y, and a z cubed. And then we have an x squared, a y, and a z to the fourth. So the first thing we have to do is identify the GCF. Start by figuring out what's the GCF of the numbers. Remember, the numbers or the coefficients, we have a 2, a 1, and a 1. Okay, well, what's the only factor in common between 2, 1, and 1? That's just a 1, all right? So there's nothing really interesting numbers-wise. They don't really have any other numbers in common. But then let's look at the individual variables. First up, how many x's do they have in common? There's 3 x's here, 2 x's here, and 2 x's here. So how many do the 3 expressions at least have? How many x's did they at least have in all 3 of them? Well, hopefully you're saying that it's the smaller exponent, x squared. There's at least 2 x's in each of these. Now let's take a look at the y's. There's a y to the first, a y to the first, and another y to the first. Well, obviously they each have at least one y in common. Then the last component is the z's. There's 3 z's in the first one, 3 z's in the second, and 4 z's in the third term here. How many z's are there in at least all of them? Well, they each have at least 3 z's in common, right? We can find at least 3 z's in each of the terms. We can find at least 1 y in each of the terms. And we can find at least 2 x's in each of the terms. Again, all we did here was we worked through each variable one at a time, and we found what the smallest exponent on the common variable was, okay? I want to point out really quick, what if this y did not exist? What if there was no y in this third expression? Then there would be no y in our GCF. The reason for that is because the GCF is the common factor. It's the thing that all of them share. If there were y's in only some of the terms, but not all of them, then we don't include it because they don't all share that factor, okay? The factors must be in each of the expressions, not just some, but all of them, okay? Well, fortunately, we do have a y in all of these cases, so we're good here. Now let's actually go and let's factor out this GCF. We're saying x squared times y times z cubed. If we take this GCF and we multiply it by something, we're going to end up with the 2x cubed y z cubed plus the x squared y z cubed minus the x squared y z to the fourth. We can go ahead and we can actually start dividing all of this. So go ahead and divide for yourself all of these by x squared y z to the third and see what you get for your final answer. Well, as you work through this, hopefully you're noticing that this is really just the process of distribution in reverse. We're saying we took this GCF and we've multiplied it by some quantity to get these 3 quantities. So what could that be? Well, let's start with the first one. Let's start with the x cubed, the y, and the z cubed. I'm going to get a little more space here. Well, how did we get a 2x cubed y and z cubed? What could we have multiplied the GCF by? Well, we could have multiplied it by a 2. Then we have an x squared that turned into an x cubed, so we got to multiply it by 1x. The y stays the same and the z stays the same, so this is going to be our first term. Now let's add on the next term. The next one has an x squared, a y, and a z cubed. That's exactly what our GCF is. So we don't need to change anything. We can just multiply that by a 1. Then let's get to the last term. It's a negative. So we multiply x squared y z cubed by some negative value to get the negative x squared y z to the fourth. Okay. X squared times what got us x squared? Well, that's just a 1, so we don't need to worry about that. y times what got us y, again, that's just a 1, don't need to worry about it. But z cubed times what got us z to the 4th. That's just a z to the 1st power. Hopefully you're noticing that this is really just the process of distribution in reverse, essentially. We're just asking ourselves, what did we have to multiply by to get these three quantities? So let's check our work. Let's make sure we got it down. X squared yz cubed times 2x. Well, that's just going to be 2x cubed yz cubed. And then let's take the GCF times 1. Well, obviously nothing changes. It's still an x squared y z cubed. And then let's take that GCF to the last term. It's going to be a negative x squared y, and then z cubed and z to the first makes z to the 4th power. Hopefully this is making sense to you. Really, it's just the process of identifying the GCF and then dividing it from each of the terms. So our final answer we can write as the GCF x squared y z to the 3rd times the polynomial 2x plus 1 minus z. That is going to be our final answer. Again, we came up with taking two unknown quantities and multiplying them together to get a larger expression. We're just using this idea of maybe they have something in common. Do all polynomials have a GCF? No. No, they don't. There are certain polynomials that will not have GCFs, such as 5x squared plus 3x minus 2. There's nothing in common there. I mean, there's a 1 in common, but that doesn't really do anything too interesting, does it? Instead, we can use this technique only when there is a GCF available. This method works when there is something in common with all of the terms. So, when do we use this method? Use this method for any sized polynomial. Use it for any type of polynomial you want, right? Binomials, trinomials, 4-term, 5-term, 6-term, whatever. Use it anytime you can. So for any sized polynomial, as long as a GCF is in common for all of the terms. Again, that won't always happen. The GCF method does not always work. In some cases, a GCF doesn't exist, and we're going to learn what to do in those cases in future videos. But if a GCF exists, if there's something in common, a factor in common between each of the three terms, then use it. Factor it out. Let's take a look at one more example. And in this case, notice that we have a little different of a setup. We have a negative value as our leading coefficient. The first thing we're seeing is this negative 24x squared. Well, let's go ahead and let's take the GCF like normal. We have a 24 and 18. We also have an x squared, a y, and then we have an x and a y squared. So pause the video, take a minute, make sure you're comfortable figuring out the GCF, and then let's check back in with your answer. All right, well, hopefully you're noticing that the 24 and the 18 have the factor of 6 in common. There's an x squared in this term, but there's an x to the first in this term. So they at least have one x in them. And then for the y's, there's a y squared here, but there's a y to the first here. So they at least have only one y in them. So 6xy is going to be our GCF. I'm going to change this around just a little bit. And I'm going to say the GCF should be negative 6xy. Here's why. if the leading term is negative, make the GCF also be negative. Okay? If the leading term is negative, make the GCF negative. The reason is we don't tend to like the GCF, or we don't tend to like the leading terms to be negative. And it's helpful when we factor them out, and we'll see later on how factoring out a negative GCF can help us when we need to simplify things later on, factoring down and simplifying rational expressions. But for right now, it's just really a practice technique to work with. So we're taking negative 6xy, multiplying it by some quantity to get negative 24x squared y to the first, and a positive 18 x to the first y squared. All right, first up, what could we have multiplied a negative 6xy by to get negative 24x squared y? Well, negative 6 and 4 makes negative 24. I have an x to the first, and I need to get an x squared, so I'll multiply it by another x. There's a y to the first and a y to the first there, so I won't do anything. So the first term in our new answer should be 4x. The next term needs to get me an 18xy squared. So negative 6 times what gets me 18? Negative 6 times negative 3 gets us positive 18. There's an x to the first and an x to the first, so I'm not going to change anything there. But I have a y to the first here and a y squared here. So I'm going to have to include an extra y. So we're saying that the factors are negative 6xy and a 4x minus 3y. Let's check our work and let's see how we did. Negative 6xy times 4x is negative 24x squared y. Negative 6 and negative 3 is positive 18. And we have an x, and the y times y is y squared. Well, what do you know? We get the exact answer we started with. Our factors for the polynomial are negative 6xy and a 4x minus 3y. Now, if you didn't factor out the negative, that's okay. That's not really an incorrect solution. It's just later on, I want you to be able to do this to simplify much more elaborate expressions where you will have to be comfortable factoring a negative out, okay? If you have any questions about this video or any comments, please let me know. My email is klinford, that's KLINFORD, @wccnet.edu. Until next time, take care.